Good morning. In today's mixed signal lecture we will discuss about the pipelined analog to digital converter. Therefore I will wrap up the successive approximation and algorithmic converter algorithm that we discussed last week, and then I will show you how we can extend this to go towards the pipeline ADC. The algorithm that we discussed last week was for this algorithmic analog to digital converter. Step 1 was to sample the input voltage. Then we compared this input voltage to 0. If the voltage is larger than 0, then we set the most significant bit to 1, and we decrement the internal voltage by Vref over 4. If not, which means if V was smaller than 0, then we set the respective bit to 0 and we increment the internal voltage. After decrementing or incrementing the internal voltage, we have the reminder, and we amplify this reminder by a factor of 4. There I explained that we scale the internal voltage, the reminder or the quantization arrow, back to the original voltage interval, and then we proceed with the next iteration cycle in this algorithm. We saw that we can plot this algorithm in this diagram and to find a graphical solution of this. Therefore we had two lines. The first line here on the right hand side, this one represents exactly the left branch here in the algorithm. So if we are larger than 0, which means that we are somewhere in this interval, then we reduce the internal voltage by Vref over 4 and amplify this by a factor of 2. And this gives us a new voltage that we use in the next iteration cycle given by this line. And in the same way here on the right hand side, if we are smaller than 0, then we increment the voltage and amplify the whole thing by a factor of 2, and this is described by this line. And the blue line was a help line for this graphical solution of the algorithm. So, do you have questions so far on what we discussed last week? Then we try to translate this into a block diagram, and this was the final slide that we had. We said here there is a control circuit implementing this algorithm, and this control circuit steers these DACs here. So we are starting with the MSB, check here for the sign, then we steer this ADC, subtract the input signal and the DAC value, and we amplify this by this factor of 2, for instance. We can also use another factor, we will see this later on. So my last question was, how can we accelerate the conversion here? Well, here the conversion time is given by going n times through this loop. So we have to check n times for the sign of the internal voltage. Then we have some delay in the control register. We have to switch the DAC, so we have to wait for the DAC settling. Then at the end we get a new voltage here, and then we have to check the sign again. So we have n DAC conversion times, and we have n comparator delays, and in good approximation we can assume that the digital delay is negligible. Okay, so everything has to be done n times. So any idea how we could accelerate this? What is done in digital design if the throughput through a signal processing circuit has to be accelerated? Did you hear anything about pipelining? Well, I guess in digital domain you are aware what pipelining is, and now we should try how we could do a pipelining for this algorithm. So let me go back to the algorithm here. Here you can see what causes n time the delay is this feedback loop. So to get rid of this factor of n, we could say, okay, let's take this algorithm here, and instead of going n times through this algorithm, we unroll this and put n yellow blocks below each other. So I go through the first yellow block, then instead of going to the input of this yellow block again, I go to the input of the next yellow block. So we have more or less something like this, several yellow blocks. And I put in data here, do the processing. I put the result then to the next stage, to the next stage, and to the next stage. And after I've put data to the next stage, I can process already new data in the actual stage. So I put this result to the next stage, and I can sample a new input for a new processing. This is the pipelining concept. I do one iteration cycle in one stage, then I pass data to the next stage, and therefore I pull in new data into my actual stage. So data ripples through these n stages step by step. So it is shifted through this stack of stages, and this is what people call a pipeline. So the question is, how can we do this in our circuit? To do the pipelining, of course, we need more sampling elements. So let's assume any circuit in between here. We have processed the data here. Then we cannot keep it constant here in a pipeline concept because we want to process new data from the input. So we have to sample the result from the first stage again to keep it constant for all subsequent stages. This means that we need this additional sampling elements. So if we start from the original converter architecture, the first thing that we have to do is that we have to break the feedback. So input data is not, so this does not mean a ground, this means that we break the feedback here, okay? Perhaps I draw it like this. So each stage is autonomous. We do not control all DACs by a global controller that is in a feedback loop, so we break the feedback. Then we have to insert these sampling elements. So what we did so far is to sample at the input, but now we have also to sample after each stage. And what is missing so far is that we cannot use this comparator for all of these stages, because now all stages work simultaneously. So we need a comparator in each stage. So we need a comparator here. Sorry. We need a comparator here. Comparator here. And okay, here we already have one. We can use this one. So somehow we increase the effort because we need these comparators in each stage and we need the additional sampling elements. But after we have this, we can enable this pipelining, which means what at the end? That we do not need n iteration cycles, but that we can latch in a new input sample in each iteration cycle. So still it means that it takes n cycle times to pass the data through the complete pipeline. So the conversion time is not accelerated. But what is accelerated is that after each cycle, new results come out of the ADC. This means after each iteration clock, new data is available. This means we have increased the throughput by a factor of n, because data arrives each cycle and not 1 out of n cycles. However, it still takes the same time until the data at the input arrives at the output. And this is an important thing that we have to distinguish between the throughput and the throughput goes up by a factor of n. And we have the conversion time, and this one is equal. People also say there is a latency along this pipeline or in this converter, because after applying data at the input it takes n cycles, but after each cycle new data comes out. So is it clear here the difference between throughput and latency or conversion time? Of course, this requires that we fill up the pipeline. So if we start processing and the pipeline is empty, then it takes n cycles until the first datum arrives at the output. So this is the latency. And then after we have filled the pipeline, then each cycle later new data arrives. Okay? Please think through this. This is a pretty important concept, not only in mixed signal or for the pipeline ADC. This is a very important concept also in the digital domain. Okay, let's simplify the circuit. And here you have a plot that illustrates again how it works. We have now n stages, and in each cycle we sample an input, process it in the stage and pass it to the next stage. Then it is processed in the second stage, and in the meantime we process a new sample in this stage. So each stage can be illustrated like this. We can say, okay, each stage is usually described like this. This is what you can find in the textbooks or very often in publications. And this is exactly the same that we had on the previous slide. So let's start here. We have for each element, we have a sampling element. We have a quantizer. The quantizer checks is it positive or negative, and depending on the result, we steer this DAC. Then we subtract the sampled signal from the DAC signal and amplify the remainder by a factor of 2. And what you can see here is exactly the same, only that it is in a somehow generalized form. We sample the input signal here. This, what is called here ADC, is the quantizer. So this is the quantizer. The result of the quantizer is passed to the DAC. Then we subtract input signal and DAC signal and amplify it by a factor of 2. So why is here written ADC and not single bit quantizer? Well, because the concept is more general than we saw it from this basic algorithm. In this algorithm we said we process in each loop cycle 1 bit. We check is it larger or smaller than 0. Of course, we can do a multi-bit decision per cycle. So we could, for instance, subdivide the original interval in 4 sub-intervals. Then we have here a 2-bit ADC. And then we convert this result back and subtract it from the input, get here the quantization error and scale this back to the original voltage range. So this is more general. We can also use here a multi-bit quantizer. But for understanding, think to this picture. We can really assume that this is a single-bit quantizer for understanding of the basic principles. Okay. When is the data valid in such an ADC? So you can see from this picture that we have here our data outputs. When can I sample my data at the output? This is also a very important and inherent property to pipelining. When is this bit valid? What do you think? After how many cycles? Okay, I will wait. Someone has to answer this. After how many cycles is this bit valid? Okay, let me start. This one is valid after the first cycle, sure, because we sample the data, we do the processing, and after this cycle, this one is valid here. Then we pass data towards the next stage. So the next bit corresponding to the first sample is valid after 2 cycles. The third bit is valid after 3 cycles, and so on and so on. So the bits corresponding to a certain input sample become valid at different times. Okay, because these bits are processed in different time steps. So at the end, we get something like this. We get here the first bit of one sample. Here we get the second bit of the previous sample, and so on. So at the end, we have to resort the bits, that all bits belonging to one word are actually delivered in one word. And this can be done by a so-called queuing circuit in the digital domain. So here you can see that we have our pipeline. This is pipelined in an analog fashion. After n cycles, the LSB of a certain sample comes out of the pipeline. However, the MSB of this conversion is valid even n cycles in advance. So we have to delay the MSB by n cycles in order to align it with the LSB. So for all intermediate bits, we need this aligning and this delaying too. However, here we need, for the MSB, we need the most delay elements, and then we come down by one delay element in each step, and finally the output stage does not need any delay element. We have therefore in this direction a digital pipeline, and this is important for queuing. Or you can say for aligning of result bits. A common failure that is done here is to say, okay, in the first stage I have to delay the result n times. So I do not take n flip-flops in series, but I take a single flip-flop and I subdivide the clock by a factor of n. This would reduce the effort considerably. However, it is totally wrong, because here in this pipeline we have a history of all previous n bits. If you would have a single flip-flop here with the divided clock, then we would have only 1 bit. So it would work, but only for every nth sample, not for all of them. So this is a big disadvantage, or hence it is a failure to have only one flip-flop here with a subdivided clock. So we really need these flip-flops. However, in the meantime, in modern technologies, digital circuitry is that small that here all these queuing flip-flops that in a block diagram look like much effort are actually a very small block in your circuit. The area still is dominated by this analog circuitry here. Okay. Yes. Pardon me? Why do we? We have twice bit. What do we mean twice bits at the output? Oh, yeah. This is. You're right. This is a failure in the picture. So this is n minus 1, and this is n. This is not 2 times bit. Can you write this down, please? Okay. Thanks for this comment. Okay. Let me discuss now what happens in this algorithm if the circuit blocks are not ideal. So let's take a look at this algorithm. So here we subtracted Vref over 4, or we added Vref over 4. And our comparison was done with respect to 0. Let's assume that this is what we plan to implement, but due to process variations, the threshold of the comparator is shifted. So let's assume that we have here not V larger than 0, but that we compare V larger than V offset. This is due to variation. Okay. Then we can, of course, still illustrate this, but now we can see that the threshold is shifted by VO. So if we are smaller than VO, then we follow this line. If we are larger than VO, then we follow this line. And you can see here that we have a region here where we leave this box of plus minus Vref over 2. So what is the impact of this? Let's do an example where we convert an input voltage that is exactly positioned in this interval. So let me choose a good color. Okay. Let me extend this one and this one. And let's start here with this voltage. Starting with this voltage means we have in this as an input sample. Then we want to compute the voltage for the next loop cycle. Therefore, we go on this curve. We can see we are below the threshold. So the left branch is the right one, and the new voltage for the next cycle is this one. And here you can see if we put this again into the algorithm, the technique was to go horizontally to the blue line. And on the blue line, we go up to our curve. So we can see this here is our new value. This is the value for the next iteration cycle. This one is on the right-hand side of the threshold. So the right branch is the valid one. And you can see that we leave this box even further, so we come even, or the distance to this plus minus Vref over 2 box is increased. And then I do the next cycle, and you can see I go out even more. Okay, this is only 2 steps, and to have this in a higher graphical quality, I have plotted this here. So you can see here the same thing for more steps. You can see we start with a value here, and if we come out of this plus minus Vref over 2 box, then in each cycle we get farther and farther off this box. What does this mean? This means that the residue, which is the quantization error, becomes larger and larger. So what we actually want is that the quantization error is reduced. As we have this gain factor of 2, it is not reduced to 0, but it should stay inside this box. And if we leave this box once, then it becomes larger and larger. So obviously the algorithm doesn't converge anymore. We can say we have here a box of convergence, and we have to stay inside this box under all circumstances. Then the algorithm works, and you can see this here from the slopes of the red and the blue curve, that this one will work stably inside the box. But here you can see that the slope or the magnitude of the that the slope is reversed. No, sorry, actually it's the same slope, but you can see here that the order is reversed, and this leads to the fact here that if the red one is above the blue one, we get farther and farther off. If it is the other way around, like here, blue one up, the red one, then we stay in this convergence box. So what is the learning here? Let me go back here. As soon as we leave this box of convergence, the algorithm does not converge anymore. Well, there is always a certain variability in a circuit. Even if you build very precise circuits, you cannot avoid that there is a certain deviation from what you have planned. Okay? So you have planned, for instance, a threshold of 0. Well, then it is always a little bit smaller or a little bit larger than 0. So it is not avoidable that if you fall in this region, maybe it is small, but it is there. But if you fall in this region, then your algorithm does not converge anymore. So somehow this ADC conversion algorithm is not robust against variations, because each variation in the threshold may lead to an error. So the question is, what does it mean if the algorithm does not converge anymore? And therefore I've plotted a converter characteristics for you. And you can see here a blue line, and the blue line is the step function, very small steps, for the case that the threshold is perfect. Here we have V larger or smaller than 0. Then we end up with the blue line here. And I have a zoom in here. Here you can see that there is indeed small steps here. Then I introduced a variation in this threshold. I said, okay, now the threshold is wrong. And you can see this leads to the red line. And the red line shows significant deviations from the ideal blue one. Well, it is interesting that there are regions where there is nearly no error. For instance, if you would zoom in here, then you would see it seems to be perfect there. And this can indeed be the case if for this particular voltage you never hit the region where you come out of the box. So for instance, if you look to this algorithm and you have a lucky voltage that avoids this region here in all cycles, then you are still perfect. But if for any cycle you come into this region, then from this point on there is a divergence. And you can see here also that the error is different in magnitude. So here you can see there is a region where the error is huge. So this is here the case when you enter this problem region already in the first cycle. Then you might have a voltage that does not fall into this region in the first cycle, but maybe in the second or third cycle. And depending on the number of cycles, when you fall in, well, your error is large or medium or smaller or even less. But it's there. So we have to find a solution that makes our conversion algorithm, this algorithm of binary search, that is quite useful algorithm, more robust against variations. Well, then people came up with an idea for this. And this was to say, okay, what happens if we choose more than one threshold? Well, choosing more than one threshold leads to the left picture. Here you can see we have not only the threshold at a position 0, but we have it also at plus Vref over 4 and minus Vref over 4. So this is something that is represented by this more general pipeline stage that I sketched. So you remember I gave you this picture. Here we had an ADC, then we had a DAC. This was subtracted, and here was the gain element. Oops. Okay, here we have a 2-bit ADC. And this 2-bit ADC is actually what determines these 3 thresholds here. Well, is this the cure? What do you think? Let me remove this again. Assuming that we have a shift in the threshold here, for instance like this, then you can see we again fall out of this convergence region. So if we are here, then we go here, here's our other line, and then there is divergence again. So this is not the solution. However, perhaps it's still not such a bad idea to have more than one threshold. Let's say we keep these 3 thresholds, but we try to stay off this boundary. This can be seen on the right-hand side. Here we have still these 3 thresholds, but you can see that the scaling factor is less. So we do not scale the residue back to full range, but we have a scaling factor that is smaller. So that's why I wrote in these pictures always A and not a factor of 2. A factor of 2 is the basic algorithm, but we can also choose another factor. So if we look on the left-hand side here, you can see we have a stage quantizer with B bit. So in this case, we have it B equal to 2. And then we have a gain factor A equal to 2 to the power of B. And then we scale the residue back to these limits. However, we are sensitive to threshold variations. On the right, we have the same. Okay, we have still B equal to 2. However, now we go not back to the full scale. So obviously, the gain our gain A is now smaller than 2 to the power of B. And what is the advantage of this? Let's assume that we have a variation in the threshold here. Let's assume we have the same variation in the threshold here. So on the left-hand side, we saw that we fall out of the convergence region. So here, well, if we have the same variation here, we are still inside the box. For sure, this is an error that we make here, but we stay in the convergence region. So we give all subsequent steps the chance to compensate for this error. So here we have a so-called redundant SAR. And this means that we are not sensitive to these variations of the threshold. And this is the way to go. This is a general thing that you have to keep in mind if you build analog or mixed signal circuits. You cannot avoid variation completely. If you spend more effort, if you spend more area, then your circuit gets better and variation is smaller. But it is still inherent in the circuit. Analog circuits that are not that do not suffer from any variations do not exist. So the goal is to build a circuit that it is not the goal to build a circuit that has zero variations, but the goal is to build a circuit that is insensitive to these variations. So, and this is a very, very good example for this, because here we see, well, there is variation. Of course, we try to keep this as small as possible, but we cannot get rid of it completely. And here we said, let's build the algorithm such that it is insensitive to a certain amount of variation. And then we get a very precise analog or mixed signal circuit that gains its robustness at the expense of additional effort in terms of algorithmic complexity, which at the end means at some digital cost, because we have to do more iterations, and we need another gain factor, and so on and so on. This is digital effort. We will see this right now. But then we get a very, very robust circuit. Well, did I miss a slide? Let me check. Yes. So unfortunately, I missed one slide. This is one I will put into your slides for the web. I will sketch it here. We can also build other stages. For instance, we can see here we have a VI, and here we have the voltage for the next cycle, VI plus 1. Here we have our convergence box. And so far we had 3 thresholds. It is also possible to have 2 thresholds. And then the curves look like this. So again, here you can see that we have a redundant pipeline stage. So we have redundant pipeline ADC algorithm. we have here two thresholds. And we have a gain A equal to 2. And this one does not scale the residue back to full scale. Well, we will see that this leads to a stage resolution of 1 bit. However, what comes out of the quantizer? Well, we have now three levels. We can say, okay, we are in region 1, we are in region 2, or we are in region 3. So this is more than 1 bit of information. Okay? This is 3 levels. It is less than 2 bits of information, which would be 4 levels. So this is somehow 1.5 bits of information here. So we have information contained in the output. And output means the output of the stage. So let's say in the stage output is 1.5 bit. Well, I said actually this stage provides 1 bit of resolution. You will understand it till the end of the lecture why it is 1 bit. But here we get 3 levels out, so we get out more information than 1 bit. And this is exactly this redundancy that leads to this robustness. So we get more information from each stage that we actually get at the end. And then we overlap this information with the results from the next stage, and in the end we get an output of only n bits, not n times 1.5 bits, but n bits, which is robust against these variations. And what we can also mention here finally, that the residue, let's say the quantization error, stays in the convergence box. And this is true even for with very strong gain or threshold variations. We stay in the box, so the algorithm converges. Okay. Let's revisit the pipeline concept in more detail to understand how these bits coming out of each stage are used to reconstruct the full result. Because here you can see we get 3 levels out. At the end, we want only 1 from this stage. So how can we compute the final result from these 1.5 bits falling out of each stage? I will explain this with this subranging ADC, and subranging here means that we only have a pipeline of 2 stages. So we have 1 stage and a second stage. And therefore, we with this structure, we can understand everything, and then we extend this to n stages, which is at the end the same. Here we can see that we have our first stage with a coarse quantizer. We convert the result back, subtract it from the input, then we scale it by a factor of A, and we pass this to the second stage, which is here called a backend ADC, because this is all the rest. The first stage provides a B out 1, and the second stage provides a B out 2. So our question is, how can we get the overall result B here? So the principle, of course, is that we have a coarse quantization in the front end, and we have a fine quantization of the quantization error. So let's say of the first stages quantization error. If you look at this structure, then we can see here we make a ADC conversion, a coarse one. We convert the result back with a DAC, and we subtract it from the sampled value. This is a picture that you saw, I guess, in the first or second lecture of this course, where we tried to extract the quantization error. This is exactly here the case. This here is the quantization error. And we scale this quantization error back and process it in the backend ADC. Then at the beginning of the ADC chapter, I showed you this slide. And here I said, well, it is not a perfect model, but it's a very useful model to assume that the ADC is something that takes the input voltage and adds some quantization noise to it. And now we will use this model to understand the subranging or the pipeline ADC. Let's assume that we model an ADC by this block. And then we can insert it in this diagram. And this leads us to a new block diagram. Oh no, here I have an intermediate slide, sorry. We want to replace this ADC in our model by this circuit. Well, here we can see, if we insert this, that we have the input voltage. The ADC is something that adds a quantization error, and this is what we subtract from the input voltage before we scale it back to A. So the output bit B, so the output of this stage, is given by the input plus the quantization error. So this is the B equal to V plus E. E is the quantization error. Okay? Then we write this down. This one is here. Okay. If we assume that we have here V plus E, and we subtracted this from V, then we get here the quantization error, or minus the quantization error, and this one is scaled by this factor of A. So at the output we have minus A times E. Minus A times the quantization error. And this is very useful to understand how we convert this back. Let's put it into the subranging circuit. here we can say we have a B out 1 given by V in, exactly the formula from the last slide, plus the quantization error EF, which is the coarse quantization error from the front end ADCs. So this is exactly this formula, okay? This one. And then we can do the same thing for the back end ADC. The back end ADC adds a quantization error EB, and the input signal of the back end ADC is the output of the front end ADC, and we have seen on the previous slide that this is A times the quantization error that we have here. So I use the second formula, which is B out 2 equal to minus A EF plus EB. Okay, now you have two outputs of the front end, one of the front end ADC, one of the back end ADC. The question is, how can we combine them? You can see both errors contain a quantization error. And to get a precise result, it is desirable to have a very small, or in the perfect case, no quantization error. So if we look at these two equations, we can think about how to get rid of the quantization error. Here I copied these two formulas. So what we can do is to say, well, we have the EF visible at the output of the first stage, and we have the EF visible at the output of the second stage. Well, here is a factor of A, but it's the same quantization error. So what we could do is to say, let's multiply this by a factor of 1 over A and add it to the first output. So what we do is we multiply result of the backend ADC by 1 over A and add it to B out 1. Then we get a B out, which is given by V in. You can see this cancels, and we have plus 1 over A times times EB. By combining the two outputs like this, we have now only the quantization error of the backend ADC. So only dependent on the quantization error of the back end. And the second important point is this quantization error is scaled by 1 over A. And this is the advantage of this technique. You might say, okay, there is still a quantization error of the backend ADC. Yes, this is right, but we scale this by a factor of A, so the quantization error of the fine ADC is reduced by this gain in the first stage. And this leads us to the resolution that we can achieve. So we know the definition of the resolution is 2 to the power of n. N is the resolution, and this is equal to the reference voltage divided by the VLSB, so the minimum voltage increment. So we can solve this for n, and this gives us n is the logarithm LD of VREF over VLSB. And the VLSB is determined by the max quantization error. And this one we know, this is 1 over A e to the power of B. So this means that we have here this equal to LD VREF over EB. And now here I have a factor of A, EB over A. And I take this A out of the logarithm and write here plus logarithm of A. And this means that we have here VREF over EB, the logarithm of this. This is the resolution of backend ADC. So this is the NB. And we have plus LDA. So in this two-stage concept, the overall resolution is given by the resolution of the backend plus the logarithm of the gain. So the contribution of the first stage is the logarithm of the gain. So now let me go back. Here we had this slide where I said in such a configuration where we have a gain equal to 2 but 3 decision levels, we get 1.5 bit information out, but at the end the stage contributes only 1 bit to the resolution. Now you know the reason. The resolution contributed by the stage is the LD of the gain, so LD2, which is 1 bit. And the additional bit is there in this computation in the digital domain to compensate for uncertainty. Here you can see how we can combine these two results. In order to do this, we multiply the second equation by 1 over A and add it to the first one. So how does this look in a circuit? In the circuit, it looks like this. We take, in the digital domain, we take the first output signal. So this was the first equation. And we add it to the second one. However, the second one is scaled by this factor of 1 over 8. Okay. So our subranging ADC is the first stage, which is a coarse ADC. The backend ADC, which is also a coarse ADC but works on the quantization error. And we have here a digital circuit that takes the bits from the first stage and the bits from the second stage and combines them in order to get the overall result. If we insert again our linear model for the ADC, for the quantizers, which means that we use this model and that we use this model, then we can compute the output signal. And the output signal here is given by B out equal to, here you can see we have the V in passed through this adder, so we see at the output a V in. Sorry, we have here a V in. We see the quantization error of the first stage passes this adder, so we see an EF here. So we have plus EF. The quantization error also passes this adder, so we have EF minus 1, so minus EF multiplied by A. So this is minus EF times A, passing this adder, passing this multiplier, experiences a 1 over A gain, and this leads us to minus, so I already put this here, this gives us a factor of minus A over AD. Let's call this 1 over AD. This is the EF. And finally, we have this quantization error of the backend ADC. Multiply this by 1 over AD and have it visible at the output. So we have plus E backend over A digital. This one is called A, the analog gain, and I called this AD, which is equal to this one, A digital, because this is one in the digital domain. So if you look at this equation, then you might ask, well, on the previous slide, he told us that we get rid of the quantization error of the first stage completely. This is what we saw here, that this EF and the A times EF in the second equation compensates because I multiply it with A and then it compensates. Well, indeed, if we say the A, the analog gain, and this digital gain is the same, then we have a factor of 1 here, so we have 1 minus 1, and this term here cancels. However, this cancels only if the A and the AD is exactly the same. And this is a difficulty, because one is a gain factor, an analog gain in an amplifier, the other one is a digital number. So the digital number can be designed very precisely and robust, but the analog gain can vary. So what we have to assure is that the digital gain always represents the analog gain. So we need a good matching between these two A's, which does not mean a matching in a layout sense, of course, but which means that the A and the AD have to be equal. So this one cancels out, this goes to 0 if A equal AD. This is the requirement that we have here. Well, what happens if we go from 2 stages to n stages? So here we had a front-end ADC and a back-end ADC. Now you can say, okay, let's do the same thing for the back-end ADC. Subdivide the back-end ADC again in a front-end and a back-end. And the resulting back-end can be subdivided again in 2 ADCs. And then you end up with normal pipeline that we have already discussed today. So we have n stages, one after another. And for each of them, we can also use this linear model. So we can build such a linear model for each stage. And this gives us a circuit like this. So we have a first stage, then we have a second stage, and so on and so on. And finally, we have really a back-end ADC, which is not subdivided anymore. Out of each stage, we get our output bits. Let's assume that we have this 1.5 bit stage, so we get this 3 levels out here, or we can also say we have really 2 bits if we have 3 decision levels and 4 intervals, and we have to recombine this. The output signal, and unfortunately I did not bring the slide which has this equation on it, so I have to write it down. We have our output signal, which is the V in. For sure, this one passes immediately to the output. Then we have the quantization error E1. And the E1 can take 2 passes. The E1 goes this way. So here we have E1 times 1. But it can pass also this way. And here we have A1. Sorry, this is minus A1 over A1 digital then we have the second quantization error, this one. Well, this one can also take 2 passes and is then scaled by a factor of 1 over A here. So we have plus 1 over A1 digital times E2 times 1 minus A2 over A2 digital. And so on and so on. I'll write it for the third stage again. Here we have 1 over A1 digital, which means that the quantization error of the first stage is scaled by this scaling factor. It is also scaled by this scaling factor. So we have here a 1 over A1 dig and A2 dig. Third quantization error times 1 minus A3 over A3 dig. And so on and so on. And finally we have our last stage, and the last stage sees all the scaling factors on the reverse way. So we have a product of AI digital, where I is equal to 1 and can go to n minus 1 times the quantization error En of the back-end ADC, which is this one. So, huge, terrible formula. But we can see in this formula, as soon as the A and the corresponding A digital, so the gain in the analog and the gain in the digital domain, as soon as they match, so if these two and these two and these two are equal, then all the intermediate terms vanish. This is our goal. We have to achieve the matching between the analog and the digital gains. And then they cancel out. So this one cancels out, this one cancels out, and this one cancels out. So this goes to 0, this goes to 0, if we achieve this matching, okay? This one goes to 0. And we have what we have at the very end is our B out, which is equal to V in, for sure. This is what we want. We want to build an ADC, plus the quantization error of the back-end ADC over the product of all gain factors. So we have here AI digital for all gain factors, which means we have the quantization error of the backend ADC and we divide it by all stage gains of the previous stages. So each stage contributes an LD of gain to the resolution, and our overall resolution R is given by the resolution of the backend ADC. So this is backend. The last one, plus the resolution, the stage resolution contributed by each stage. So we have to sum over all stages. And we have seen that the stage resolution is the logarithm of the gain. So we have the LD of the stage gain. So what we see here, really, the gain elements determine the resolution, not the number of bits or the number of decision levels coming out of each stage. Make this clear. So the basic pipeline ADC means we compute in each cycle each bit. Okay, this was what these basic algorithms at the beginning showed. Then we saw this is somehow sensitive to variations. We need redundancy. And the redundancy unfortunately leads to the fact that a certain bit weight comes not out of only one stage, that we can say, okay, the MSB comes always out of the first stage and the fourth bit comes only from the fourth stage. No, it is created by this computation, by combining all the results together and doing this digital arithmetics, scaling the bits coming out of the particular stages by this digital A's and summing them together. This is how we then at the end get the overall output word. So the final question is, I want to mention here the effective stage resolution Ri. This is what you already know, is the logarithm of the stage gain. Okay. The final question for all this is, how can we assure that the A and the A digital match? You can cite me and say, okay, he said everything has some variation, so also the gain has some variation. If we implement the digital gain, it is fixed. So we run into trouble here, because then the intermediate terms do not vanish. What we can do is that we try to measure the analog gain. And say, okay, we have implemented the chip. Now there is a certain gain. We have to measure it and adjust the digital gain to this measurement. And this measuring and adjusting, this is what people call a calibration required for the pipeline ADC. And one among many possibilities to calibrate the pipeline ADC is shown here. Here you see in the upper part exactly the pipeline stage that we have discussed so far. And then we can say, okay, here there is a gain, and we want to get this, we want to know this gain. What you can do is to inject a signal here, and this signal here is quantized in the ADC and becomes visible here. This signal is not only quantized by the ADC, but then it is also converted back into the analog domain by this DAC, passes here, is scaled by a factor of A, and then it goes through all other pipeline stages and through the backend ADC, and it comes back here. So at this point we have the signal injected here, and we have the signal injected here, scaled by A, and then we have it here. So here we have an additional factor of AD. So we have the direct signal scaled by AD, we have the signal through the backend ADC scaled by a factor of A, and if A and AD match, then the difference of these two signals should be 0. If they do not match, then we have to adjust the A digital until they do match. Well, now you might say it is not desirable to add, to insert an additional signal anywhere in the circuit. This must disturb the operation of the ADC. And in order not to disturb the operation is to say, okay, we generate here a noise signal. And we put this noise signal while the ADC is doing its normal operation. We add this noise signal here. Then it is visible here. It becomes visible here. And then we can adjust the AD. However, now if we have the regular signal coming from the input here, and we have the test signal, which is the noise signal, then we have both of these signals in parallel, and we have to separate them. And therefore, people invented this correlator which says, okay, we know the noise, we take the signal coming here, subtract the signal coming from here, and we correlate it from the noise to the noise, which means the input signal is not correlated from the to the noise. This one cancels out. The signals coming here and here are strongly correlated to the noise. So by using this correlator, we can extract only the test signal, and we can use this test signal to tune the digital gain. Well, what you can see here is that the circuits become quite complex and complicated if you want to go robust. So we started with this very basic algorithm, which was a binary search. Then we saw that we can run into problems if we have variations. We found a countermeasure, which requires a much more difficult digital post-processing. And then we saw that there is a matching requirement, and this matching requirement for very precise converters also requires a calibration. And then I showed you this one possibility of calibration. So you see robustness, which at the end means high resolution and precise circuits. If you want to do this, then you can see that complexity and effort grows considerably. However, in this field, there is still lots of innovation possible. If you say, okay, how can I make circuits robust? How can I make calibration techniques to get around certain impairments or certain variability? There is still lots of room for innovation here. Okay, in general, we can say a calibration technique. Well, this is what I showed you, is one example for a particular class of converters, namely the pipeline ADC. Calibration is more general. It can be applied in several fields of circuit design, and it is always divided in two phases. So first you have to estimate the error, and then if you know the error, you can try to compensate. Well, there is analog approaches. The first techniques for calibration was analog approaches, where I say, okay, I measure my error and then I adjust the gain by adding some cap or by adding some resistance to a node, and by doing analog tuning. However, this approach is somehow limited and also costs some effort, because and causes also some trouble, because by adding this calibration elements, you add additional analog circuit elements which cause parasitic capacitance, which may cause noise, which cause area, and so on. So the more modern techniques are purely digital techniques that do not try to improve the circuit, but that try to do an intelligent signal processing on the results, so that you can get a good accuracy even with not too accurate analog circuits. Well, here on this picture you can see several classes of calibration. The easiest one is the foreground calibration. And foreground calibration means you start up your system, you know there's some problem, then you measure, insert some test signals, measure the failure, and compensate for it. And after you have done this, you say, okay, now I turn off my test signal and I have a regular mode of operation. Well, this is easy, sure, but it requires that you have this startup phase, this correction phase at the beginning. And if the error develops over the operation period, for instance, because of the voltages change or the temperature changes or whatever, then you have no chance to react on these additional errors, because you have done the calibration at the beginning, and from this point on, you run the system. Therefore, you can say, okay, I want a background calibration. A background calibration is like the one I explained, is one that runs into the background, runs in parallel the normal operation in such a way that it does not disturb the normal operation, but it's active all the time. So if something happens during your operation of the system, the background calibration adjusts this and compensates for this. There is also two ways. The true background calibration is one as the one I showed you, which uses the actual hardware and runs in a tricky way that does not interfere with the normal one. For instance, using noise, which is then extracted by correlation. There is also a virtual background calibration, and this can be in the context of the pipeline ADC, for instance, that you say I have n pipeline stages and I implement n+1. And I always take one offline, calibrate it, and after it is calibrated, I place it into the signal path again, take another one offline, calibrate this one. Here you can see, well, this requires additional circuit elements because I need one extra pipeline stage, yes? And it also requires some means of switching circuit blocks to take one out, put another one in, and so on. So this is also some more effort. So the desirable way is always to have a true background calibration. This is the goal. Well, it's not always achievable, but if you find a tricky solution to have it in the background, in a true background way, then this is very advantageous because then you can react all the time without the need for additional elements. Okay. Let me conclude the pipeline chapter. We saw that stage errors can be tolerated as long as the residue stays in this convergence box. Or at least it should be scaled back into this or come back to this convergence box before we reach the final ADC. We have talked about words like latency, throughput, and I hope you got the difference here and saw the advantage of the pipeline ADC. So that the pipeline ADC is more or less the same as a successive approximation algorithm, which is unrolled. So it does not run in a loop, but it runs through a sequence of n times the same block. We can see here that the number of blocks increases linear with the resolution. So if we want additional bits, then we need additional stages. It does not grow, and this is a big advantage. It does not grow exponentially. Next week we will talk about the flash ADC, which is the fastest ADC that you can implement. So this is really the top speed ADC. However, this is a very expensive ADC in terms of hardware per bit because it grows exponentially, and this means we are limited to a small resolution and a low number of bits. Well, and we have seen that all of this pipelining stuff lives from the fact that we can implement precise sample and hold elements, because this is the elements we need additionally in each stage if we unroll this binary search algorithm. Okay, that's it for today. If you have questions, I will be around for some minutes, and I hope you have much fun with the tutorials and have a nice week. Thank you.